Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring the profound and awe-inspiring process of how black holes are born, from the majestic death of massive stars to their ultimate gravitational collapse. Before we gently immerse ourselves in this cosmic transformation, I would like to know where you are at this moment. Perhaps you are nestled by a window, watching the gentle rhythm of falling rain, or maybe you are simply wrapped in a warm blanket, listening to the soft hum of your surroundings. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The journey into the heart of a black hole's birth begins paradoxically with life, with the luminous existence of a star far more massive than our own sun. These colossal stellar engines are the true alchemists of the cosmos, spending millions of years in a delicate dance of forces. Deep within their fiery cores, hydrogen atoms, under immense pressure and unimaginable temperatures, are fused together to create helium. This process, known as nuclear fusion, releases an astonishing amount of energy, which radiates outward, creating a powerful pressure that perfectly counteracts the relentless inward pull of the star's own gravity. This state of equilibrium, where the star is stable and shining brightly, is what we call the main sequence phase of its life. It is a long, steady burn, a period of profound stability that shapes the very fabric of its existence. As a massive star ages, it begins to exhaust the hydrogen fuel in its core. With less hydrogen to fuse, the core starts to contract, growing denser and hotter. This compression ignites new layers of fusion, causing the star to swell dramatically into a red supergiant, a truly immense, luminous entity that dwarfs anything in our solar system. Within this swollen behemoth, the fusion process continues, moving up the periodic table. Helium atoms fuse into carbon, carbon into oxygen, and so on, creating a layered structure within the star, much like an onion, with progressively heavier elements forming in concentric shells towards the center. Each new element requires even greater temperatures and pressures to fuse, a testament to the star's incredible internal power. This grand stellar alchemy continues until the star's core is predominantly composed of iron. And it is here that the majestic life of a massive star reaches its most critical juncture. Iron presents an insurmountable barrier in the star's fusion process. Unlike lighter elements, fusing iron atoms together does not release energy. Instead, it consumes energy. This is a fundamental principle of nuclear physics, a cosmic wall that no star can breach through fusion alone. Once the core becomes saturated with iron, the star can no longer generate the outward pressure needed to resist the crushing force of its own immense gravity. The delicate balance that sustained it for millions of years is irrevocably broken. The core, no longer able to support itself, begins to collapse with terrifying speed. In mere milliseconds, it shrinks from a sphere the size of Earth to a compact object just tens of kilometers across. This swift inward plunge is an event of unparalleled violence and energy, culminating in what scientists describe as the iron catastrophe. The core's collapse is so rapid and extreme that it rebounds, sending powerful shockwaves tearing through the star's outer layers. This catastrophic explosion is a Type II supernova, an event so luminous that for a brief period, a single dying star can outshine an entire galaxy of billions of stars. The supernova blasts vast quantities of matter and newly forged heavy elements, including gold, silver, and uranium, out into the interstellar medium, enriching the cosmos with the building blocks for new stars, planets, and indeed, life itself. These scattered elements become the stardust from which future generations of cosmic structures will form. But what remains of the star's core after such a cataclysmic event? Its fate is determined by a single critical factor: its mass. If the remnant core after the supernova retains a mass greater than approximately 2 to 3 times that of our Sun, a threshold known as the Tolman-Oppenheimer-Volkoff limit, then no known force in the universe can halt its continued gravitational collapse. Not even the immense pressure of degenerate neutrons which supports neutron stars is enough. Gravity, now unopposed, becomes the sole dominant force. The core continues to shrink, compressing itself into an infinitesimally small, infinitely dense point, known as a singularity. As this singularity forms, it warps the very fabric of space-time around it so profoundly that a boundary emerges, the event horizon. This is not a physical surface, but rather a region of space-time from which nothing, not even light, can escape. It is the point of no return, a cosmic threshold where the familiar laws of physics, as we understand them, begin to transform, guiding all matter and energy toward the singularity. This profound transformation from a star's brilliant life to its final quiet collapse beyond the event horizon is the birth of a stellar black hole. It is a cosmic monument to gravity's ultimate power, a silent, unseen testament to the universe's endless cycles of creation and transformation. Having witnessed the dramatic birth of a stellar black hole, our gaze now turns to its intrinsic nature, to understand what truly defines these enigmatic entities. At their heart lies the singularity, an infinitely dense point where the entirety of the black hole's mass is concentrated. For a non-rotating black hole, this singularity is often conceived as a single point in space, a concept first mathematically explored by Carl Schwarzschild. However, if the progenitor star possessed a significant spin, which most stars do, the resulting black hole is a rotating Kerr black hole, and its singularity takes the form of a ring. This subtle difference in geometry at the very core suggests that the universe's fundamental laws of physics, particularly general relativity, are pushed to their absolute limits, and perhaps even beyond, within these extreme environments. Surrounding this singularity is the event horizon, a concept we briefly introduced. It is a boundary, a one-way membrane in space-time, not a physical surface that one might touch or feel. Instead, it represents the precise radius at which the escape velocity from the black hole's gravitational pull equals the speed of light. Anything that crosses this threshold, whether it be light, matter, or even information, is inexorably drawn inward, unable to ever return. Imagine a boat caught in a river whose current gradually increases. At some point, the current becomes stronger than the boat's maximum speed, and no matter how hard the engine pushes, the boat is carried downstream. The event horizon is precisely this point, but for light and everything else. It is a boundary where the familiar arrow of time itself seems to align solely with the direction towards the singularity. A profound and irreversible cosmic journey. The existence of a black hole, then, is predominantly defined by these two features, its singularity and its event horizon. Yet, despite their profound gravitational influence, black holes are characterized by surprisingly few properties. This elegant simplicity is encapsulated in what physicists refer to as the no-hair theorem. This theorem, a cornerstone of black hole physics, posits that once a black hole has formed and settled, it can be entirely described by just three observable classical properties: its mass, its angular momentum, or spin, and its electric charge. All other information about the matter that collapsed to form it, such as its chemical composition, its temperature, or its complex internal structure, is thought to be irretrievably lost behind the event horizon. It is as if the black hole retains only these bare essentials, shedding all its hair or distinguishing features, making each black hole of the same mass, spin, and charge absolutely identical. The immense gravitational field of a black hole profoundly. This curvature is far more extreme than that caused by any other celestial object. Imagine space as a stretched rubber sheet. A star would create a gentle dimple, but a black hole would punch an infinitely deep well. This distortion of space-time has several astonishing implications. One of the most striking is time dilation. For an observer far from a black hole, time appears to slow down dramatically for anything approaching the event horizon. A clock ticking near the event horizon would appear to tick slower and slower to a distant observer, eventually seeming to freeze entirely at the boundary, though for the infalling object, time continues at its normal pace. This is not merely an optical illusion, but a physical reality dictated by Einstein's theory of general relativity, a profound testament to the universe's dynamic and relative nature of time. Another consequence of this extreme space-time curvature is the phenomenon known as tidal forces. If an object, or indeed a person, were to approach a black hole, the gravitational pull on the part of the object closer to the black hole would be significantly stronger than on the part farther away. This differential force would stretch the object, elongating it like spaghetti. For a human, this spaghettification would occur long before reaching the event horizon of a stellar mass black hole, as the forces would become unbearable. However, for supermassive black holes, the event horizon is much larger, and the gravitational gradient across a person's body would be less extreme at the boundary itself, meaning one could theoretically cross the event horizon without immediate bodily harm, only to face the singularity within. This thought experiment, while chilling, helps us understand the sheer scale of gravitational gradients near these cosmic leviathans. These theoretical descriptions of black holes are compelling, but how do we, from our distant vantage point, confirm their existence if they are by definition invisible? While we cannot directly observe the black hole itself, its profound gravitational influence on its surroundings provides unmistakable clues. The accretion disk, for instance, is a swirling vortex of gas and dust drawn in by the black hole's gravity. As this material spirals inward, friction heats it to millions of degrees, causing it to emit intense X-rays and other forms of radiation that can be detected by our telescopes. These luminous disks are often the brightest objects in a galaxy, a cosmic beacon marking the presence of an otherwise unseen devourer of light. Furthermore, the orbits of nearby stars can reveal the presence of a compact, invisible mass. By observing how stars are pulled into unusually tight or rapid orbits around an empty point in space, astronomers can infer the existence of a black hole, calculating its mass based on these gravitational dances. More recently, the detection of gravitational waves from merging black holes by instruments like LIGO and Virgo has offered direct evidence of their existence and dynamics, a symphony of space-time ripples confirming these celestial giants. This indirect evidence has become increasingly robust, confirming the reality of these space-time distortions and inviting us to ponder the profound interplay between mass, energy, and the very fabric of reality itself. Beyond the stellar remnants we have explored, the universe hosts an even grander spectrum of black holes, each born through distinct yet equally profound cosmic processes. These celestial enigmas remind us that the gravitational abyss is not a singular phenomenon, but a diverse family, playing varied and indispensable roles in the grand narrative of existence. If the stellar mass black holes are the silent, dense hearts of individual collapsed stars, then the supermassive black holes are the colossal anchors around which entire galaxies whirl, centers of immense gravity quietly shaping the destiny of billions of stars and countless worlds within their vast gravitational embrace. These gargantuan entities, residing at the very heart of nearly every large galaxy, including our own Milky Way, boast masses ranging from millions to even tens of billions of times that of our Sun. Such an incredible concentration of mass in a relatively small volume prompts a fundamental question. How do they come into being so early in cosmic history? The formation of supermassive black holes remains one of the most compelling mysteries in astrophysics, with several leading theories vying for scientific consensus. One prominent idea suggests that they might originate from the direct collapse of immense, pristine gas clouds in the very early universe. In these primordial conditions, vast reservoirs of hydrogen and helium gas, unhindered by strong stellar winds and intense radiation, could have cooled efficiently and collapsed directly into black holes, bypassing the typical stellar formation phase entirely. This rapid pathway would elegantly explain their observed presence in the very early universe, where observations of distant quasars, extremely luminous galactic nuclei powered by actively feeding supermassive black holes, indicate their existence just a few 100 million years after the Big Bang. These ancient behemoths, already so massive, suggest a swift and potent genesis, a testament to the universe's capacity for rapid, large-scale structure formation. Another compelling hypothesis proposes that supermassive black holes grow from smaller stellar mass black hole seeds through a relentless process of accretion. Over billions of years, these initial black holes would slowly but steadily accumulate enormous quantities of surrounding gas, dust, and even entire stars, effectively eating their way to supermassive status. This steady diet of cosmic material would cause them to swell, drawing in matter with an efficiency that defies our terrestrial understanding of consumption, converting a significant portion of the infalling mass into energy, which then powers the luminous activity of active galactic nuclei. Mergers with other black holes, particularly during the violent epochs of galactic collisions, would also contribute significantly to their growth, adding to their already immense gravitational dominion. Imagine two galaxies, each harboring a central black hole, slowly spiraling towards one another in a cosmic waltz, driven by gravity's irresistible pull. The eventual fusion of these two cosmic behemoths would release a torrent of gravitational waves, a powerful ripple in the very fabric of space-time, signaling the birth of an even larger, more powerful supermassive black hole. Indeed, the existence of such mergers has now been directly observed through gravitational wave astronomy by observatories like LIGO and Virgo, offering tantalizing glimpses into this violent yet ultimately formative aspect of cosmic evolution, a profound confirmation of the universe's capacity for such grand, destructive unions and the dynamic growth of its most massive objects. Beyond the stellar and supermassive varieties, theoretical physics also entertains the concept of intermediate mass black holes, often referred to as the missing link in the black hole family tree. These elusive objects are hypothesized to possess masses ranging from a few hundred to several hundreds of thousands of solar masses, neatly bridging the vast gap between their smaller stellar and larger supermassive counterparts. Their existence is less definitively confirmed than other types, presenting a fascinating challenge for astronomers, but observations of ultra-luminous X-ray sources in certain galaxies and the dynamic behavior of stars in dense globular clusters provide intriguing indirect evidence of their potential presence. The prevailing theories for their formation often involve runaway collisions of massive stars within these extremely dense stellar nurseries, where stars are packed so closely that gravitational interactions can lead to repeated mergers, eventually forming a black hole of intermediate mass. Alternatively, they could arise from the successive mergers of numerous stellar mass black holes, slowly accumulating enough mass to reach this intermediate scale, a slower, more patient path to growth within the stellar metropolis of a cluster. The ongoing search for definitive proof of intermediate mass black holes continues to promise a deepening of our understanding of black hole evolution and the gravitational landscape of the universe, revealing more about the intricate pathways of cosmic development and the various scales at which gravity can assert its ultimate dominion. And then there is the most speculative yet profoundly intriguing category: primordial black holes. Unlike all other types, these are not thought to form from the collapse of stars. Instead, they are hypothesized to have originated in the very first moments after the Big Bang, from extreme density fluctuations in the nascent, rapidly expanding universe. In this incredibly hot and dense early epoch, regions of space-time with slightly higher than average density could have collapsed under their own gravity to form black holes, ranging in size from the truly microscopic, perhaps even at the Planck mass, to masses comparable to stars or even larger. These primordial black holes, if they exist, could potentially account for a portion of the universe's mysterious dark matter, providing a unique and elegant solution to one of cosmology's greatest puzzles, the unseen scaffolding of the cosmos. While no direct observational evidence for primordial black holes has yet been found, the possibility remains a vibrant area of theoretical research, contemplating a universe where black holes are not merely the end products of stellar evolution, but also ancient relics from the dawn of time itself, silent witnesses to the universe's very first breath and the subtle imperfections that shaped its earliest moments. Their potential presence invites us to consider the universe's initial conditions with even greater wonder, knowing that the seeds of extreme gravity might have been sown in the earliest instance of cosmic time. Thus, we see that black holes, far from being uniform cosmic voids, are a diverse population, each type emerging from the universe's grand processes in its own distinct way. From the fiery demise of colossal stars to the slow, relentless growth in galactic centers and even the fleeting, dense moments of the early cosmos, these gravitational singularities serve as powerful reminders of the extreme conditions and profound transformations that shape our reality. They are not merely destroyers, but also sculptors, catalysts for creation, and enigmatic witnesses to the universe's ongoing evolution, woven into the very fabric of cosmic time. In their silent presence, we find a profound reflection of the universe's vast and mysterious depths, a calm invitation to ponder our own place within this ever-unfolding story, knowing that even the greatest darkness holds a unique and essential light, a constant force of shaping and change in the ceaseless dance of the cosmos. Our exploration into the various origins of black holes naturally leads us to ponder their ongoing lives within the cosmic tapestry. Once formed, these gravitational behemoths are not static objects. They continue to evolve, interacting with their surroundings in ways that profoundly shape galaxies and the universe itself. The growth of black holes is a dynamic process, primarily driven by two fundamental mechanisms: accretion and mergers. Accretion, the gradual infall of gas and dust from the surrounding environment, can slowly but steadily increase a black hole's mass. This process is most spectacularly observed in active galactic nuclei, where supermassive black holes at the centers of galaxies consume vast amounts of matter, creating intensely luminous phenomena as the infalling material heats up to extreme temperatures before crossing the event horizon. The accretion disk itself is a marvel of cosmic physics, a swirling maelstrom of plasma moving at relativistic speeds. As particles within this disk rub against each other, they generate immense friction, causing the disk to glow brightly across the electromagnetic spectrum, from radio waves to powerful X-rays and gamma rays. This radiation is not merely a byproduct, it also exerts a pressure, pushing away some of the surrounding gas, creating a delicate feedback loop that regulates the growth of both the black hole and its host galaxy. This complex interplay suggests a profound, almost symbiotic relationship between supermassive black holes and their galactic homes, where the growth of one often influences the evolution of the other, binding their destinies in a cosmic dance of creation and regulation. Beyond accretion, black holes also grow through the dramatic process of merging with other black holes. Such events are among the most energetic phenomena in the universe, involving two black holes spiraling inward, accelerating to incredible speeds, and ultimately coalescing into a single, more massive black hole. These cataclysmic unions are the primary source of gravitational waves, ripples in the fabric of space-time, predicted by Albert Einstein's theory of general relativity. The detection of these waves by observatories like LIGO and Virgo has opened a new window into the universe, allowing us to hear the cosmic echoes of these mergers, confirming not only the existence of black holes, but also their dynamic interactions. Each detected merger offers invaluable data, allowing scientists to probe the extreme physics of gravity and the fundamental properties of black holes with unprecedented precision, revealing the universe's most violent dances in a silent symphony of space-time. But even black holes, these ultimate gravitational prisons, are not eternal. A profound theoretical prediction made by Stephen Hawking in the 1970s suggests that black holes slowly evaporate over incredibly vast timescales through a quantum mechanical process now known as Hawking radiation. This concept marries the realms of general relativity and quantum mechanics, two pillars of modern physics that usually operate independently. The vacuum of space, far from being truly empty, is constantly bubbling with pairs of virtual particles and antiparticles spontaneously popping into existence and annihilating each other almost instantaneously. Near the event horizon of a black hole, however, it is possible for one particle of such a pair to fall into the black hole while its partner escapes into space. To a distant observer, this escaping particle appears as genuine radiation emitted by the black hole, carrying away a tiny amount of its mass and energy. Over eons, this slow leakage of energy causes the black hole to shrink, eventually leading to its complete evaporation. The rate of Hawking radiation is inversely proportional to the black hole's mass, meaning smaller black holes evaporate much faster than larger ones. A stellar mass black hole would take an unimaginable number of years, far longer than the current age of the universe, to completely dissipate, while a supermassive black hole would take even longer. This theoretical death of a black hole, a gentle fade into nothingness, offers a contemplative perspective on the transient nature of even the most extreme objects in our cosmos, a testament to the universe's intricate and often paradoxical laws. This concept of black hole evaporation also brings forth a deep theoretical puzzle known as the black hole information paradox. If information about the matter that falls into a black hole is truly lost behind the event horizon, and the black hole then evaporates through Hawking radiation, what happens to that information? Quantum mechanics dictates that information can never be truly destroyed, only transformed or scrambled. This apparent conflict between general relativity, which suggests information loss, and quantum mechanics, which demands information conservation, represents a significant challenge to our understanding of the universe's fundamental laws. Scientists continue to explore various theoretical solutions, including the holographic principle, which suggests that information might be encoded on the event horizon itself, or that the information is released in some subtle form during the final stages of evaporation. This ongoing paradox underscores the profound mysteries that black holes still hold, pushing the boundaries of our knowledge and inviting us to reconcile these two magnificent yet seemingly incompatible descriptions of reality. In contemplating the evolution and eventual fate of black holes, we are reminded of the universe's relentless dynamism. From their violent stellar births to their slow quantum evaporation, black holes are not static monuments but active participants in the cosmic cycle. They grow, they merge, they radiate, and eventually they too may vanish, leaving behind only the memory of their gravitational presence. This journey through their existence, from fiery genesis to a whisper of light, reflects the transient yet endlessly transformative nature of all things, even within the profound silence of the cosmos. It invites us to consider our own fleeting existence within this grand, ever-changing dance of matter and energy, a quiet reminder that even the deepest voids are part of an ongoing story, forever unfolding. The universe in its vastness continues to reveal the silent, powerful presence of black holes through ever-advancing observational techniques. While these cosmic entities remain, by definition, invisible, their profound influence on light and matter around them paints a clear picture for our instruments. One of the most breathtaking achievements in recent astrophysics is the direct imaging of a black hole's shadow. The Event Horizon Telescope, a global network of radio telescopes, achieved this remarkable feat, first in 2019 with the supermassive black hole at the center of Galaxy Messier 87, or M87, and later with our own Milky Way's central supermassive black hole, Sagittarius A star. What we observe is not the black hole itself, but a dark silhouette against the superheated glowing plasma that swirls around its event horizon. This luminous ring of light, bent and distorted by the black hole's extreme gravity, vividly traces the boundary of no return, offering a tangible window into the heart of these space-time warps. It is a powerful confirmation of Einstein's general theory of relativity in its most extreme regime, allowing us to visualize the theoretical predictions with stunning clarity, transforming abstract equations into observable reality. Beyond direct imaging, other observational methods provide compelling evidence for black holes across the cosmos. Gravitational lensing, for instance, offers an indirect yet powerful way to detect these invisible giants. When a black hole passes between a distant light source, such as a galaxy or a quasar, and an observer on Earth, its immense gravity can bend and magnify the light from the background object. This creates distorted, multiple, or even ring-shaped images of the distant source, a phenomenon akin to looking through a warped glass lens. By carefully analyzing these distorted images, astronomers can deduce the mass and location of the intervening black hole, even if it emits no light itself. This elegant technique allows us to infer the presence of objects that would otherwise remain entirely hidden, revealing the subtle yet profound ways that gravity shapes our view of the distant universe. It is a cosmic trick of light, revealing the unseen architects of space-time. X-ray binaries provide another crucial line of evidence for stellar mass black holes. These systems consist of a normal star orbiting a compact invisible companion. If the companion is a black hole, its powerful gravity can strip gas from the outer layers of the nearby star. This gas then forms an accretion disk around the black hole, heating up to millions of degrees as it spirals inward. At these extreme temperatures, the gas emits copious amounts of X-rays, which can be readily detected by orbiting X-ray telescopes. The characteristic flickering and intense X-ray emission patterns from these binaries are strong signatures of a black hole's presence, providing a dynamic laboratory for studying accretion processes and the behavior of matter in extreme gravitational fields. This cosmic interplay of light and shadow, matter and gravity, allows us to piece together the profound story of black hole existence, even across vast cosmic distances, offering a glimpse into the dynamic ballet of binary star systems. The recent dawn of gravitational wave astronomy has further revolutionized our understanding of black holes. As we discussed, the merger of two black holes generates space-time ripples that propagate across the universe, detected by instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo. These detections provide direct, unambiguous evidence of black hole existence and their dynamic interactions. Each chirp of gravitational waves carries a wealth of information about the masses, spins, and orbital characteristics of the merging black holes, allowing scientists to test general relativity with unprecedented precision and explore the universe's most violent events. These gravitational wave signals are not merely observations. They are direct recordings of space-time itself being profoundly disturbed and then settling back into a new configuration, a testament to the elegant yet dynamic geometry of our cosmos. Beyond their individual properties, black holes, particularly the supermassive ones, play a critical role in the evolution of entire galaxies. Far from being mere passive absorbers of matter, these central engines are deeply intertwined with the life cycles of their host galaxies. The powerful jets of high-energy particles and radiation, often launched from the vicinity of active supermassive black holes, can heat and expel vast quantities of gas from the galactic center. This feedback mechanism can regulate star formation, preventing galaxies from producing too many stars too quickly and shaping their overall structure and evolution. Without this influence, galaxies might develop very differently, potentially becoming far more uniform or exhausting their star-forming gas prematurely. Thus, black holes, in their seemingly destructive nature, act as cosmic sculptors, influencing the birth and death of stars on a galactic scale, guiding the grand architectural development of the universe itself, a subtle yet profound cosmic influence that connects the smallest particles to the largest structures. As our understanding of black holes deepens, so too do the lingering mysteries and the exciting avenues for future research. The nature of the singularity itself, where general relativity breaks down, remains a profound challenge, hinting at the need for a unified theory of quantum gravity that can reconcile the laws of the very large with the laws of the very small. The precise mechanisms for the formation of primordial black holes and their potential contribution to dark matter continue to be actively investigated. Furthermore, the black hole information paradox, the apparent conflict between information conservation in quantum mechanics and information loss in classical black hole theory, continues to be a fertile ground for theoretical exploration, pushing physicists to develop new frameworks for understanding reality at its most fundamental level. These unanswered questions are not limitations, but rather invitations, beckoning us deeper into the heart of cosmic enigma. In contemplating these profound cosmic entities, their formation, their dynamic lives, and their eventual theoretical fade, we are offered a unique lens through which to view our own existence. Black holes, in their extreme nature, remind us of the universe's boundless capacity for wonder and the intricate, often counterintuitive laws that govern all of reality. Our ability to conceptualize, observe, and mathematically describe these distant, unseen objects speaks volumes about the human intellect and our innate drive to understand the cosmos. We are, in a very real sense, the universe reflecting upon itself, seeking to comprehend its most profound and beautiful mysteries. Each new discovery about black holes, each new theory, deepens not only our scientific knowledge, but also our profound sense of connection to the vast, evolving story of existence. Our journey through the origins and observed properties of black holes now leads us to contemplate their profound implications for the very fabric of reality and our understanding of the universe's most fundamental laws. These cosmic entities are not merely celestial objects. They are living laboratories where the most extreme conditions exist, pushing the boundaries of physics and challenging our deepest assumptions about space, time, and matter. They serve as a constant reminder that our current theories, while remarkably successful, are still incomplete, particularly when confronted with the immense gravitational forces at play within these enigmatic voids. Black holes stand as the ultimate tests for Albert Einstein's general theory of relativity. The predictions of space-time curvature, time dilation, and gravitational lensing, which seem so abstract, become tangible realities in their vicinity. Every observation, from the precise orbital dances of stars around galactic centers to the direct imaging of event horizons by the Event Horizon Telescope, acts as a rigorous validation of Einstein's magnificent framework. Yet, it is at the very heart of a black hole, at the singularity, that general relativity encounters its limits. Here, the equations break down, predicting infinite density and infinite curvature, a clear signal that a deeper, more complete theory is required, one that can seamlessly merge gravity with the quantum realm. This is the grand quest for quantum gravity, a quest in which black holes play a central, indispensable role, acting as cosmic guideposts, pointing us towards the next great revolution in physics. The black hole information paradox, which we touched upon, is perhaps the most compelling of these conceptual challenges. It pits the fundamental principle of quantum mechanics, that information is never truly lost, against the predictions of general relativity, which suggest that information about matter falling into a black hole might be irretrievably destroyed as the black hole evaporates via Hawking radiation. Imagine burning a book. The book's information is scrambled into ash and smoke, but it is not destroyed. In principle, it could be recovered. But if a black hole truly destroys information, then it violates this core quantum tenet. This paradox has spurred decades of intense theoretical work, leading to fascinating ideas such as the holographic principle, which suggests that the three-dimensional information within a black hole might actually be encoded on its two-dimensional event horizon, much like a hologram. This thought, initially conceived in the context of black holes, has now expanded to suggest that our entire universe might be a holographic projection from a lower dimensional boundary, a truly mind-bending possibility that reshapes our perception of reality itself. The quest to resolve the information paradox and unify general relativity with quantum mechanics leads physicists down pathways of profound theoretical speculation, exploring concepts like string theory and loop quantum gravity. String theory, for instance, proposes that elementary particles are not point-like but rather tiny, vibrating strings, and that black holes could be incredibly complex, tangled configurations of these strings. Loop quantum gravity, on the other hand, suggests that space-time itself is not continuous, but is composed of discrete, indivisible loops, or quanta. Both approaches attempt to describe the universe at its most fundamental level, where space-time ceases to be smooth and continuous, and quantum effects become dominant. Black holes, with their singularities representing a breakdown of classical space-time, offer a crucial testing ground for these ambitious theories, providing the extreme conditions necessary to probe the very nature of reality at the Planck scale, the smallest possible scales of existence, where the fabric of the cosmos is thought to reveal its true, granular nature. Furthermore, black holes continue to serve as cosmic engines for some of the most powerful phenomena in the universe. The active galactic nuclei, powered by supermassive black holes accreting matter, are responsible for enormous jets of plasma that can extend for millions of light years, profoundly influencing the intergalactic medium and the evolution of galaxy clusters. These jets, traveling at nearly the speed of light, are cosmic accelerators, injecting vast amounts of energy into their surroundings and playing a vital role in the distribution of matter and heat throughout the universe. Understanding the mechanisms behind these powerful outflows is crucial to comprehending the large-scale structure of the cosmos, revealing how these unseen gravitational behemoths act as dynamic architects, shaping the universe far beyond their immediate gravitational pull, linking their existence to the grand, sweeping narrative of cosmic evolution and the distribution of all structure. As we continue to develop new observational tools and refine our theoretical frameworks, the mysteries surrounding black holes will undoubtedly continue to unravel. Future gravitational wave observatories, such as the Laser Interferometer Space Antenna, or LISA, will be able to detect the mergers of supermassive black holes, offering even deeper insights into their growth and the dynamics of galactic evolution. Advanced X-ray telescopes will provide sharper views of accretion disks, while new theoretical models will continue to push the boundaries of quantum gravity and the information paradox. These ongoing endeavors are not just about understanding black holes. They are about understanding the universe in its entirety, from its smallest quantum fluctuations to its grandest cosmic structures, and ultimately our own place within its unfolding story. In the gentle quiet of this moment, consider these profound gravitational entities. They are not merely destructive forces, but fundamental components of the universe, shaping its evolution, challenging our intellect, and inspiring a sense of wonder that transcends our everyday experience. To contemplate black holes is to engage with the deepest questions of existence, to recognize the intricate dance of forces that governs reality, and to feel a calm, profound connection to the cosmic processes that have shaped everything, including ourselves. Our journey through the diverse origins and observed characteristics of black holes has brought us to the very edge of current scientific understanding, where these celestial phenomena reveal profound implications for the fundamental laws governing our reality. These cosmic enigmas are not merely distant objects of fascination. They are crucial crucibles where the theories of the very large and the very small collide, offering unparalleled insights into the universe's deepest workings. They challenge our most cherished assumptions about the nature of space, time and information, urging us to seek a more complete and unified picture of existence. One of the most persistent and intellectually stimulating challenges presented by black holes is the information paradox. As we previously noted, quantum mechanics insists that information cannot be truly destroyed, only transformed or diffused. Yet, Stephen Hawking's theory of black hole evaporation suggests that a black hole, after consuming matter and eventually radiating away, leaves behind only thermal radiation, seemingly devoid of the original information about what fell into it. This apparent contradiction, a deep clash between general relativity and quantum theory, forces us to confront a profound inconsistency at the heart of physics. If information is indeed lost, it implies a fundamental flaw in quantum mechanics, or perhaps a radical rethinking of how we perceive space-time itself. This paradox has been a fertile ground for theoretical exploration, prompting some of the most imaginative and groundbreaking ideas in modern physics, pushing our minds to reconcile these two magnificent frameworks, and perhaps glimpse a deeper truth about the universe. In an effort to resolve this paradox, physicists have explored several intriguing possibilities. One such concept, the fuzzball model, posits that black holes are not singular points of infinite density surrounded by empty event horizons, but rather quantum mechanical objects with a finite size, resembling a ball of strings or quantum fuzz. In this view, there is no true singularity or event horizon in the classical sense. Instead, the entire region is a complex quantum state that retains all the information of the infalling matter. This radical idea suggests that the information is never truly lost, but rather stored within the intricate quantum structure of the fuzzball itself, allowing it to eventually radiate away with Hawking radiation, thus preserving quantum unitarity. It transforms the serene, dark abyss into a vibrant, quantum-entangled entity, a testament to the unexpected ways in which quantum mechanics might reshape our understanding of extreme gravity and the nature of these cosmic behemoths. Another compelling theoretical framework seeking to bridge the gap between general relativity and quantum mechanics is string theory. In this elegant yet complex model, elementary particles are not point-like objects, but rather one-dimensional vibrating strings. Black holes, within this context, are not simply geometric distortions, but rather incredibly intricate arrangements of these fundamental strings. String theory provides a natural framework for the holographic principle, which suggests that the information contained within a volume of space, such as a black hole, can be fully described by data residing on its boundary, the event horizon. This implies that our three-dimensional reality, and indeed the two-dimensional surface, much like a three-dimensional image emerging from a two-dimensional film. This profound idea, a cosmic hologram, challenges our intuitive perception of reality and dimensions, offering a tranquil yet intellectually stimulating perspective on the universe's hidden depths and the interconnectedness of its fundamental constituents. The ongoing quest to understand black holes also drives the development of new frontiers in observational astronomy. Future generations of telescopes, both ground-based and space-based, will push the limits of resolution and sensitivity, offering even sharper views of event horizons and the dynamic environments around them. Imagine peering into the very heart of distant galaxies with unprecedented clarity, witnessing the swirling accretion disks and the powerful jets emanating from supermassive black holes in exquisite detail. Furthermore, the burgeoning field of multi-messenger astronomy, which combines observations from gravitational waves, electromagnetic radiation, and possibly even neutrinos, promises a holistic understanding of black hole phenomena. By triangulating data from these different cosmic messengers, scientists can build a more complete picture of black hole mergers, their host environments, and their impact on the universe's evolution. Each new observation is not just a data point. It is a whispered secret from the cosmos, revealing more about the profound processes that shape our existence and the hidden elegance within the universe's grand design. As we gently drift into these contemplations, the existence and mysteries of black holes serve as a powerful reminder of the ever-unfolding nature of scientific discovery. They are not simply destructive forces, but catalysts for intellectual growth, pushing humanity to question, to innovate, and to expand the boundaries of our knowledge. In their silent gravitational embrace, we find a profound reflection, a calm and contemplative journey into the heart of everything. Our journey through the diverse origins, profound properties, and deep theoretical implications. Indeed, in their silent, majestic presence, black holes invite a deep, contemplative reflection on our place within the grand cosmic narrative, reminding us of the subtle beauty found even in the universe's most extreme manifestations, a testament to the universe's elegant complexity. Black holes, in their seemingly destructive nature, are also profound cosmic recyclers and architects on scales that are truly humbling. The immense gravitational pull of supermassive black holes at galactic centers drives powerful outflows and relativistic jets of high-energy particles and radiation. These energetic phenomena can sweep away vast quantities of gas from a galaxy, preventing it from forming too many stars too quickly. This feedback mechanism acts as a finely tuned cosmic regulatory process, a delicate interplay that balances the rate of star formation, ensuring that galaxies evolve in a coherent and sustainable manner over cosmic eons. Without this profound influence, galaxies might develop very differently, perhaps becoming overly dense and exhausting their star-forming fuel prematurely, or conversely, failing to ignite new stellar generations altogether. In this sense, black holes act as cosmic gardeners, subtly pruning and shaping the growth of galaxies, ensuring the grand, intricate ballet of cosmic evolution continues. They are not simply voids, but dynamic forces that actively participate in the grand, intricate ballet of cosmic evolution, silently shaping the destinies, connecting the fate of the smallest quantum fluctuations to the largest structures in the universe. Moreover, the matter that eventually falls into black holes is not truly lost from the universe in a fundamental sense, even with the perplexing black hole information paradox in play. The energy associated with this infalling matter contributes to the black hole's increasing mass, subtly influencing its gravitational field and the surrounding space-time. And through the profound theoretical process of Hawking radiation, first proposed by Stephen Hawking, this mass is eventually returned to the universe, albeit in the form of thermal radiation, over timescales that stagger the imagination, far exceeding the current age of the cosmos. This intricate cycle, from stellar formation and collapse, through accretion and mergers, to eventual evaporation, underscores a deep cosmic principle of transformation rather than ultimate annihilation. It suggests that nothing in the universe is truly static or truly ends. Instead, everything is perpetually engaged in a process of change, a continuous flow of energy and matter, constantly reshaping itself into new forms and structures. This understanding can bring a quiet sense of continuity, a profound realization that even the most extreme cosmic events are part of an endless, majestic dance, a serene unfolding of cosmic destiny that encompasses all of creation. The contemplation of black holes, with their bending of space-time and their mysterious singularities, profoundly expands our human perception of reality. We are accustomed to a world governed by linear time and three spatial dimensions, where objects have definite locations and properties that remain consistent and predictable. Yet, black holes introduce us to a realm where these familiar intuitions break down, where time can slow to a crawl near the event horizon. Space can become infinitely warped into a singularity, and the very concept of inside and outside takes on new, mind-bending meanings. Imagine a journey where your sense of now becomes entirely subjective, dependent on your proximity to such a gravitational well, where a single moment for you could encompass eons for a distant observer, a truly relativistic experience. This intellectual journey into the extreme physics of black holes challenges our anthropocentric views. reminding us of the universe's inherent complexity and its boundless capacity for phenomena that lie far beyond our everyday experience. It cultivates a sense of intellectual humility, acknowledging the vastness of the unknown, while simultaneously fostering a deep appreciation for the power of scientific inquiry to illuminate even the most elusive corners of the cosmos, inviting us to find a quiet, profound beauty in the incomprehensible and the utterly alien, a gentle nudge toward accepting the universe's deeper truths. Perhaps one of the most beautiful and deeply personal aspects of studying black holes is the insight it offers into the interconnectedness of all things, extending even to our own existence. The very atoms within our bodies, the fundamental elements that constitute our planet, the air we breathe, and the water we drink, were forged in the hearts of stars that lived and died billions of years ago. The gravitational collapse of some of these ancient massive stars led to the formation of black holes, which in turn influenced the distribution of those life-giving elements and the formation of subsequent generations of stars and galaxies, including our own solar system. We are, quite literally, products of this cosmic history, intimately linked to the forces and phenomena that shape the universe, including the dramatic processes that give birth to black holes. This realization can evoke not a sense of insignificance in the face of such grandeur, but rather a profound wonder and awareness that our thoughts and our consciousness are an integral part of this same grand fabric of existence, a fleeting yet meaningful pattern in the endless, intricate dance of the universe. We are not separate from this cosmic ballet. We are an integral, conscious part of it, capable of reflecting upon its wonders and its deep mysteries. The ongoing scientific endeavor to unravel the mysteries of black holes continues to inspire generations of researchers, pushing the boundaries of technology and theoretical thought to unprecedented levels. From the intricate mathematical frameworks of general relativity, which first predicted their existence, to the cutting-edge engineering of gravitational wave detectors and the global collaboration behind Event Horizon telescopes, humanity's pursuit of knowledge about black holes is a testament to our collective curiosity and our unwavering desire to understand our place in the cosmos. Each new discovery, each refined model, is a step further into the unknown, a deeper communion with the fundamental laws that govern reality, revealing more about the universe's majestic elegance and its inherent order, even in the face of such extreme and seemingly chaotic phenomena. This persistent inquiry, this quiet yearning to comprehend the ultimate truths of the cosmos, is a hallmark of our species, a gentle reminder of the intellectual journey we are all on, a journey that never truly ends, but continually expands our horizon of understanding. Ultimately, black holes invite us to a deeper contemplation of the universe as a dynamic, interconnected system where creation and destruction are two sides of the same cosmic coin, constantly in motion, constantly transforming. They are symbols of transformation, of matter and energy being reshaped under the most extreme conditions imaginable, only to potentially contribute to the formation of new stars, new planets, and new cosmic structures over unimaginable eons. This profound understanding can bring a sense of calm, knowing that even in the face of such immense power and mystery, there is an underlying order and a continuous, harmonious cycle. It allows us to view the universe not as a collection of disparate events, but as a single, flowing narrative, where every star's life and death, every black hole's birth and evolution, plays a vital, irreplaceable role. In this tranquil reflection, we can find a quiet peace, a gentle assurance that we are part of something far grander than ourselves, a conscious flicker in the infinite expanse, eternally connected to the cosmic dance, drifting gently towards the silent embrace of sleep. As we allow these profound reflections on black holes to settle within our minds, we find ourselves at a fascinating juncture of scientific inquiry, where the known gives way to the profoundly speculative. The mysteries these cosmic behemoths present are not merely puzzles to be solved, but deep questions that touch upon the very nature of existence itself. compelling us to look beyond our current understanding and imagine what truly lies beneath the fabric of space-time. Here, at the ultimate limits of gravity, our most successful theories of the universe, general relativity and quantum mechanics, cease to comfortably coexist, signaling the need for a deeper, more unified description of reality. At the heart of every black hole lies the singularity, a point where density and space-time curvature become infinite according to general relativity. This mathematical infinity is not a physical reality we fully comprehend, but rather an indication that our current laws break down in such extreme conditions. It is precisely at this point that quantum effects are believed to become paramount, requiring a theory of quantum gravity to describe what truly happens. Imagine trying to describe the intricate dance of subatomic particles using only the laws that govern the movement of planets. The scales are simply too disparate. The singularity is the ultimate test, the cosmic laboratory where such a unified theory, a grand reconciliation of the universe's two great intellectual pillars, must ultimately prove its worth. Without it, the interior of a black hole remains shrouded in conceptual darkness, a realm beyond our current grasp. This theoretical breakdown at the singularity opens up a realm of profound and often speculative possibilities, inviting physicists to imagine what might truly lie beyond the event horizon. One such idea, deeply rooted in mathematical solutions to Einstein's equations, is the concept of a wormhole. A wormhole, in essence, is a hypothetical tunnel through space-time, connecting two distinct regions of the universe, or perhaps even two different universes, much like a shortcut through a vast cosmic landscape. While the classical solutions suggest that such wormholes would be unstable and collapse almost instantaneously, quantum gravity might offer mechanisms to stabilize them, allowing for, in theory, transit. It is a thought that evokes images of cosmic shortcuts, of journeys across unimaginable distances or into entirely new realities, a quiet echo of the universe's potential for interconnectedness on scales we can barely conceive. Building upon the idea of wormholes, some theorists have even posited that black holes could be gateways to baby universes or alternate dimensions. In this highly speculative framework, the singularity within a black hole might not be an endpoint of destruction, but a point of genesis, where new universes bud off from our own, expanding into their own separate spacetimes. This concept suggests a universe that is not isolated, but part of a vast interconnected multiverse, a cosmic family tree where new realities are constantly being born from the extreme gravitational collapse of matter. While this idea remains firmly in the realm of theoretical physics, lacking any observational evidence, it offers a breathtaking vision of cosmic fertility, where the ultimate acts of gravitational collapse are intricately linked to the continuous creation of new worlds and new realms of existence, quietly unfolding beyond our observable horizon, a profound testament to the universe's boundless creativity and its unending capacity for self-renewal. This journey into the extreme and speculative aspects of black holes ultimately leads us back to a contemplation of our own existence and our place within this grand cosmic drama. The very fact that we, as conscious beings, can ponder such profound questions, can devise theories and build instruments to probe the nature of these distant, invisible objects, speaks volumes about the human spirit, becoming aware of itself, reflecting upon its own origins, its own future, and its most enigmatic features. The relentless pursuit of knowledge about black holes, despite their distance and their seemingly alien nature, is a testament to our innate curiosity, our deep-seated desire to understand the fundamental truths that govern all of reality. It is a quest that transcends generations, a continuous unfolding of discovery that connects us all to the vast, intricate tapestry of the cosmos. Consider for a moment the profound implications if any of these theoretical possibilities were to be confirmed. If wormholes were found to be stable, or if evidence for baby universes emerged from black hole physics, our understanding of space-time, causality, and even existence itself would be irrevocably transformed. The boundaries of what we consider possible would expand dramatically, inviting new questions and entirely new fields of inquiry. Even the ongoing work on the information paradox, whether it leads to fuzzballs or holographic realities, reshapes our fundamental understanding of how information is stored and processed at the most extreme scales. These are not merely scientific details, they are philosophical revelations touching upon the deepest questions about the nature of reality and our perception of it. The universe, through its black holes, continually whispers secrets that challenge and expand our consciousness, gently guiding us towards a more holistic and profound understanding of everything. In this quiet reflection, we acknowledge that the universe is far more intricate and mysterious than our everyday senses perceive. The processes of stellar death and gravitational collapse, while dramatic, are part of a larger, elegant cosmic ballet that continues to unfold around us, shaping galaxies, influencing the distribution of matter, and even giving rise to the conditions necessary for life. Black holes born from the magnificent demise of stars are not merely endpoints, but pivotal nodes in this cosmic narrative, embodying both the destructive and creative forces of the universe. Their study is a testament to humanity's enduring quest for knowledge, a journey that offers profound insights into the interconnectedness of all things and our own fleeting yet deeply meaningful place within the infinite expanse of space and time. As we now turn our gaze towards the most distant cosmic horizons, contemplating the ultimate fate of these enigmatic entities, and by extension, the universe itself. These gravitational titans, born from the spectacular deaths of stars or the primordial fluctuations of the early cosmos, are not merely present in the universe. They are destined to become its longest-lived inhabitants, silent witnesses to an unimaginable expanse of cosmic time long after the last star has faded. In the far distant future, billions and even trillions of years from now, the universe will be a profoundly different place. Galaxies, once vibrant with star formation, will have largely dispersed due to the accelerating expansion of space, driven by dark energy. The vast reservoirs of gas and dust, the raw material for new stars, will be exhausted or flung too far apart to coalesce. The last red dwarf stars, burning their nuclear fuel with an almost unimaginable frugality, will eventually exhaust themselves, fading into cold, dark, white dwarfs. In this era, known as the degenerate era, the cosmos will be populated by these stellar remnants: white dwarfs, neutron stars, and predominantly black holes. They will be the enduring monuments of a bygone age of light and activity, drifting through an ever-expanding, increasingly empty void, their silent presence a testament to gravity's enduring power. Black holes will continue their slow, relentless growth even in this dimming universe, primarily through two mechanisms. Firstly, they will occasionally consume the sparse matter that drifts their way, slowly increasing their mass through accretion, albeit at a rate far less spectacular than in their youth. Secondly, and more significantly, they will grow through mergers. As stellar remnants lose energy over immense timescales through gravitational interactions, some will eventually fall into the gravitational embrace of a black hole. More dramatically, in the hearts of galaxy clusters, where black holes are more numerous, gravitational encounters will eventually lead to the merger of these colossal objects, forming increasingly massive black holes. These mergers, though rare in such a desolate future, will be the most dynamic events in the universe, sending ripples of gravitational waves across the vast emptiness, a final fading echo of cosmic violence in an otherwise tranquil, cold expanse. However, even these seemingly eternal gravitational prisons are destined to vanish. As we discussed, Stephen Hawking's profound theoretical prediction of Hawking radiation dictates that black holes slowly, almost imperceptibly, evaporate. This quantum mechanical process, where virtual particle-antiparticle pairs near the event horizon result in one particle escaping as radiation while its partner falls in, means that black holes leak energy and mass over time. The rate of this evaporation is extraordinarily slow, especially for supermassive black holes. A black hole with the mass of our Sun would take roughly 1 followed by 67 zeros years to evaporate. For a supermassive black hole with 1 billion solar masses, this timescale stretches to 1 followed by 100 years. These numbers are so immense that they defy human comprehension, making the current age of the universe, approximately 13.8 billion years, seem but a fleeting instant in comparison. This black hole era will eventually give way to the dark era, a period of ultimate cosmic stillness. After all black holes have evaporated, the universe will be left with an incredibly dilute soup of photons, neutrinos, electrons, and positrons, drifting ever further apart in an expanding, almost perfectly cold vacuum. There will be no stars, no galaxies, no black holes, no heat, and no activity. Entropy will have reached its maximum, and the universe will be in a state of ultimate thermodynamic equilibrium, a state often referred to as the heat death of the universe. In this final profound stillness, time, as we understand it, marked by change and events, might lose its very meaning. It is a contemplative rather than a frightening end, a serene descent into an ultimate quiet, where all the vibrant activity that once filled the cosmos has gently, slowly, faded into an enduring, peaceful void. The contemplation of such a distant, cold, and empty future, dominated by the rise and eventual evaporation of black holes, can be surprisingly calming. It offers a unique perspective on the transient nature of all things, including ourselves and our vibrant, complex world. Our lives, our planet, our sun, and even our galaxy are but brief, beautiful flickers within this immense cosmic timeline. Yet, the very fact that we exist in this golden age of stars, capable of observing and understanding these profound cosmic processes, imbues our fleeting existence with a unique and precious significance. We are the universe, momentarily aware of itself, capable of reflecting upon its own grand story, from its fiery birth to its eventual quiet fade. This awareness connects us to the fundamental forces that shape reality, allowing us to find a deep, tranquil peace in the knowledge that we are an intricate, conscious part of this vast and magnificent cosmic dance. In this deep understanding of black holes, from their violent genesis to their slow quantum evaporation, we uncover a profound narrative of cosmic transformation. It is a story not of simple destruction, but of matter and energy constantly being reshaped, of forces interacting across unimaginable scales of space and time. Black holes are not just cosmic monsters, but essential elements in this ongoing process, silent architects of galactic evolution and eventual harbingers of the universe's ultimate, serene stillness. This grand perspective invites us to embrace the calm wonder of the cosmos, to find peace in its vast cycles, and to rest with the profound knowledge that we are intrinsically connected to the universe's timeless, elegant unfolding. Our extensive journey through the intricate birth, enigmatic nature, and profound implications of black holes now draws us toward a final contemplation, a synthesis of the cosmic dance we have observed. We have traversed from the fiery heart of a collapsing star, through the silent space-time warping presence of the event horizon, to the theoretical whispers of quantum evaporation and the grand galactic architecture influenced by these gravitational titans. What emerges is not merely a collection of scientific facts, but a deeper, more holistic understanding of the universe as an intricately woven tapestry of interconnected processes, where even the most extreme phenomena play an indispensable role, shaping the very essence of reality and inspiring profound intellectual wonder, beckoning us to look deeper into the cosmic unknown. Black holes serve as cosmic lighthouses, not by emitting light, but by illuminating the boundaries of our current understanding. They stand as the ultimate testaments to the power of gravity, confirming the elegant predictions of Einstein's general relativity in ways that even he could scarcely have imagined. Yet it is precisely at their heart, within the singularity, that this magnificent theory reaches its conceptual limits. This breakdown is not a failure, but a profound invitation, a clear signal from the cosmos that our intellectual journey is far from over. It beckons us towards a grander synthesis, seamlessly describe both the vast, smooth curvature of spacetime and the chaotic, probabilistic dance of the quantum realm, reconciling these two seemingly disparate pillars of modern physics. The search for this elusive theory, inspired by the profound mysteries of black holes, represents the next great frontier in our quest to understand the universe at its most fundamental level, a silent, intellectual beacon guiding generations of scientific inquiry, promising revelations that will redefine our cosmic perspective and reshape our deepest intuitions. The very existence of black holes compels us to reconsider our intuitive understanding of reality. We live in a world where time flows uniformly and space offers predictable dimensions. But within the gravitational embrace of a black hole, these familiar concepts are radically transformed. Time becomes relative in the most extreme sense, potentially slowing to an apparent standstill for distant observers, while space itself is stretched and compressed into an infinitely dense point. Such phenomena remind us that our everyday perception is but a narrow window into a far more complex and dynamic cosmos. It encourages what remains ingenuity of the human mind to conceptualize and measure these alien realities. To ponder these distortions is to engage with the universe on its own terms, to accept its strange beauty, and to expand the very horizons of our conscious experience, finding a calm, profound wonder in the unexpected and the utterly magnificent, a serene invitation to embrace the unknown. Moreover, the interplay between black holes and their galactic environments reveals a universe that is not a static collection of isolated objects, but a dynamic, self-regulating system. Supermassive black holes, once thought to be mere passive centers, are now understood as active architects, influencing the birth and death of stars, the distribution of gas, and the overall evolution of entire galaxies through their powerful jets and feedback mechanisms. This intricate relationship underscores a fundamental principle of cosmic interconnectedness. The smallest quantum fluctuations, the life and death of individual stars, and the growth of colossal black holes are all part of a single, majestic, unfolding story. Every element, every particle, every gravitational interaction plays a role in shaping the grand cosmic tapestry, weaving together a narrative of continuous change and profound order. This profound realization can bring a deep sense of belonging, a quiet assurance that we are not separate observers, but integral participants in this continuous, elegant dance of creation and transformation, forever interwoven with the universe's destiny. The persistent mysteries surrounding black holes, from the information paradox to the potential existence of wormholes and baby universes, are not roadblocks to understanding, but rather powerful engines of discovery. They invite us to speculate, to theorize, and to develop new observational techniques that will push the boundaries of what is currently possible. The ongoing efforts in gravitational wave astronomy, the groundbreaking images from the Event Horizon Telescope, and the continuous refinement of theoretical models are all part of this grand scientific adventure. Each unanswered question acts as a gentle whisper from the cosmos, beckoning us further into its depths, promising revelations that will not only deepen our scientific knowledge, but also profoundly reshape our philosophical understanding of what it means to exist within such a vast and wondrous reality, expanding the very frontiers of human thought and consciousness. Ultimately, the study of black holes is a testament to humanity's boundless curiosity and our unique capacity for abstract thought. Our ability to grasp such extreme concepts, to model phenomena that transcend direct human experience, highlights the extraordinary nature of consciousness itself. It reminds us that we are not just collections of stardust, but conscious arrangements of that stardust, capable of contemplating the very processes that gave rise to us. In this contemplation, we find a profound sense of peace, a realization that our individual existence, while fleeting, is part of an eternal cosmic narrative, deeply interwoven with the universe's most majestic and mysterious forces. This connection can evoke a tranquil sense of belonging, a calm satisfaction in the knowledge. As we gently bring our contemplation of black holes to a close, let us carry with us this profound understanding. These magnificent, silent architects of space-time are more than just cosmic anomalies. They are integral to the universe's grand narrative. From the explosive birth of stars that seed the cosmos with elements for life, to the intricate dance of galaxies, all shaped by the unseen hand of gravity. Their mysteries, far from being unsettling, serve as gentle invitations to explore the deepest layers of reality, to marvel at the elegant, often paradoxical laws that govern existence. Consider the quiet resilience of matter, transforming through fire and collapse, eventually returning its essence to the cosmic ocean. Ponder the intricate balance between creation and destruction, a ceaseless rhythm that orchestrates the universe's majestic evolution. And in this vast, interconnected tapestry, remember your own place. You are a part of this cosmic story, a conscious observer capable of comprehending its wonders. A fleeting yet deeply meaningful flicker in the eternal dance of energy and existence. May these deep thoughts about the birth, life, and ultimate fate of black holes carry you into a world of tranquil sleep. Remember that the universe is amazing, and you are a part of it. Fall asleep with this feeling of serenity, profound connection, and endless knowledge. Good night. The journey into quantum entanglement begins in a realm where the familiar rules of our macroscopic world gently dissolve, giving way to a reality far more subtle and interconnected than we might intuitively grasp. Imagine, if you will, two tiny particles, perhaps a pair of photons or electrons, born from the same event, sharing a profound, invisible bond. This is the essence of quantum entanglement. These particles, no matter how vast the distance separating them, remain intrinsically linked, their fates intertwined in a way that defies our classical understanding of space and time. It is this peculiar connection that once led Albert Einstein to famously describe it as spooky action at a distance. To truly appreciate the depth of this strangeness, let us consider a fundamental property of these quantum entities: spin. For an electron, for instance, its spin can be measured as either up or down along a particular axis. However, before any measurement is made, the electron does not possess a definite spin. Instead, it exists in a state of superposition, a wondrous blend of both up and down simultaneously, a cloud of probabilities rather than a fixed reality. It is as if the particle is poised at a crossroads, undecided, holding all possibilities within its quantum nature. Now, picture two such electrons, let us call them Alice and Bob, which have become entangled. They might have originated from the decay of a single atom, sharing a common history that binds them. According to the laws of quantum mechanics, if Alice's electron is measured to have a spin up, then Bob's electron, no matter how far away it might be, across a room, across a galaxy, or even at the very edge of the observable universe, will instantaneously be found to have a spin down when measured along the same axis, and vice versa. The correlation is absolute, immediate, and without any discernible communication between the particles. It is as if they know each other's state, instantly adjusting their own to complement their partners, defying the very notion of separation. This instantaneous correlation was precisely what so deeply troubled Einstein and his colleagues, Boris Podolsky and Nathan Rosen, leading them to formulate what is now known as the EPR paradox in 1935. Their argument was elegant and seemingly logical. If a measurement on one particle immediately influences the state of another distant particle, it would imply a transfer of information faster than the speed of light. This, they reasoned, would violate the principle of locality, a cornerstone of physics which states that an object can only be directly influenced by its immediate surroundings, and that no information can travel faster than light. Such a violation would undermine the very fabric of special relativity, a theory Einstein himself had pioneered. To resolve this apparent paradox, Einstein, Podolsky, and Rosen proposed that quantum mechanics must be an incomplete theory. They suggested that there must exist hidden variables, some unknown, pre-existing properties or instructions carried by the particles from the moment of their entanglement. These hidden variables, they posited, would predetermine the outcome of any future measurement, meaning that the particles' states were never truly indefinite. Instead, they were simply unknown to us, like two sealed envelopes, each containing a secret instruction opened only upon measurement. If this were true, there would be no spooky action, no instantaneous communication, only the unveiling of a pre-established reality. The particles would simply be following their pre-programmed destiny, much like two perfectly synchronized watches that always show the same time without ever needing to communicate. Consider a simple analogy to illuminate this idea. Imagine you have two perfectly matched gloves, one left and one right. You place each glove into a separate, identical box, seal them, and then send one box to a distant friend. Before your friend opens their box, they do not know whether they have the left or the right glove. The glove inside exists in a state of uncertainty, a kind of classical superposition of possibilities. However, the moment your friend opens their box and finds, say, the left glove, you instantly know that the glove in your box must be the right one, even if you are millions of miles apart. There is no spooky action at play here. The correlation exists because the gloves were always a pair, their properties determined from the outset. Einstein and his colleagues believed that entangled quantum particles behaved in a similar predetermined fashion, guided by these elusive hidden variables. Yet, this deeply intuitive idea that reality is fundamentally local and real in the way we perceive it would soon face its own profound challenges. The universe, at its smallest scales, seemed to resist such straightforward interpretations. The implications of this debate between an intrinsically uncertain, interconnected quantum reality and a more classical, predetermined one extend far beyond the laboratory. They invite us to ponder the very nature of what is real, what is knowable, and whether our perception of independent objects is merely an emergent property of a deeper, unified existence. In contemplating this quantum dance, we are gently reminded that the cosmos holds secrets that continue to reshape our understanding of ourselves and our place within its grand, mysterious unfolding. Character count, 7,998. The intuitive allure of hidden variables, offering a comforting classical explanation for quantum correlations, was indeed strong. This perspective sought to preserve a universe where properties existed independently, waiting only to be revealed, not created, by observation. Yet, this deeply ingrained classical view would face a rigorous, almost poetic challenge. A challenge born from the ingenious mind of an Irish physicist named John Stuart Bell. In 1964, Bell devised a theoretical framework, now famously known as Bell's theorem, which provided a profound and elegant way to test whether Einstein's spooky action at a distance was merely a symptom of an incomplete theory, as Einstein believed, or if it truly pointed to a deeper, more unsettling, non-local reality. Bell's work was not a rejection of Einstein's profound insights, but rather a brilliant refinement, pushing the boundaries of what we could empirically verify about the quantum world, moving beyond philosophical debate into the realm of experimental proof, a testament to the power of scientific inquiry. Bell's theorem, though rooted in intricate mathematics, can be understood in its profound implications without delving into its complex equations. It essentially posits that if local hidden variables truly exist, if the particles predetermine their outcomes before any measurement, without any instantaneous, faster-than-light communication, then the statistical correlations between entangled particles, when measured in specific, carefully chosen ways, should always conform to a certain maximum limit. This limit, known as Bell's inequality, sets a precise boundary on how strongly correlated the outcomes of distant measurements can possibly be, if only local predetermined properties are at play. Imagine, for instance, a game of chance with two players, each holding a card from a pre-shuffled deck. The cards are correlated because they came from the same deck, but the act of one player looking at their card does not instantaneously change the other player's card. Their properties were fixed from the moment the cards were dealt. Bell's inequality describes the maximum level of correlation expected in such a classical predetermined scenario. If, however, quantum mechanics is correct and particles genuinely exist in a state of indefinite possibilities until measured, then these correlations could, in theory, exceed that classical limit. It was a brilliant stroke of insight, transforming a centuries-old philosophical debate about the nature of reality into a concrete, experimentally verifiable question, a clear and decisive fork in the road for our understanding of the cosmos, urging us to look beyond our everyday perceptions. For many decades, the technological prowess required to perform these exquisitely delicate experiments with sufficient precision was out of reach. The challenges were immense, creating entangled pairs of particles reliably, sending them over distances great enough to rule out any classical light-speed communication, and then measuring their properties without inadvertently disturbing their delicate quantum states. All of this had to be achieved while ensuring the experimental setup itself did not introduce any hidden classical correlations. But in the 1980s, a pioneering French physicist named Alain Aspect and his team, working in Paris, conducted groundbreaking experiments that began to provide definitive answers. They generated pairs of entangled photons and sent them to detectors separated by distances that made any classical light-speed communication impossible within the brief measurement time frame. Imagine these elusive photons traveling silently through the laboratory, their fates meticulously interwoven, a ballet of unseen connections. By precisely measuring the polarization of these photons along various rapidly changing axes, they gathered data to test Bell's inequalities against the predictions of quantum mechanics. The results were startlingly clear and consistent. The correlations observed consistently violated Bell's inequalities, aligning perfectly with the predictions of quantum theory. This was a monumental finding, a quiet yet profound revolution, suggesting that the particles were indeed exhibiting a connection that could not be explained by the comforting intuitive notion of local hidden variables. It was a subtle whisper from the quantum realm, confirming its inherent strangeness and demanding a reevaluation of our most fundamental assumptions about reality. Since Aspect's pioneering work, a global effort has seen countless experiments performed, each more refined than the last, systematically closing various loopholes that skeptics initially identified. These included the locality loophole, which questioned whether the detectors were truly far enough apart to prevent even the fastest hypothetical light-speed communication from influencing the outcomes. Another significant challenge was the detection loophole, which worried about whether a truly representative sample of particles was being measured, or if only the easy-to-catch ones were skewing the results, creating a false impression of entanglement. Modern experiments, some stretching over hundreds of kilometers using optical fibers, involving billions of entangled pairs and even using light from distant quasars as random number generators, have now closed these loopholes with astonishing confidence, reaching levels of certainty that are difficult to dispute. The consistent conclusion, supported by decades of robust experimental evidence, is that entanglement is a real, fundamental, and undeniably non-local feature of our universe. The quantum world does not operate under the comforting assumption of local realism. This means that either locality, the idea that objects are only influenced by their immediate surroundings and that no information travels faster than light, or realism, the idea that properties exist independently of measurement, or perhaps both, must be profoundly reconsidered in the face of this quantum truth. This powerful realization forces us to confront a profound choice in our understanding of the cosmos. Most physicists, in light of the overwhelming experimental evidence, have come to accept that locality, in the classical sense, does not hold at the quantum level when it comes to entangled particles. It is not that information is traveling faster than light, which would fundamentally break special relativity, but rather that the entangled particles exist as a single, indivisible quantum system. Their properties are not individual, but relational, defined only in reference to each other, even when separated by immense cosmic distances. The universe, at its most fundamental level, exhibits a deep, inherent interconnectedness that transcends the spatial boundaries we perceive. It is as if the universe itself, in certain intricate arrangements, prefers to operate as an unbroken whole rather than a collection of independent parts. To clarify why this spooky action does not permit faster-than-light communication, consider our entangled pair, Alice and Bob, each with their electron. Alice measures her electron and finds it to be spin up. Instantly, she knows Bob's electron, if measured along the same axis, would be spin down. But Alice could not choose her electron to be up. The outcome of her measurement is fundamentally random, governed by quantum probabilities. She cannot force her electron to take a specific spin value to send a predetermined signal to Bob. Since she cannot control her outcome, she cannot impose a message. Bob, receiving his electron, observes a down spin, but this outcome, from his perspective, is also entirely random. Only by later comparing their results, perhaps via a classical light-speed message or phone call, can they confirm the perfect correlation. This means no information, in the sense of a controllable message, ever travels faster than light. The universe safeguards its speed limit even in the face of such profound quantum intimacy. It is a revelation, a quiet understanding that the fabric of reality is far more subtle and intricate than our everyday experiences suggest, weaving together distant points in a tapestry of shared quantum states. The implications of this non-local interconnectedness extend far beyond mere philosophical curiosity. They are actively shaping the technological frontiers of our era. One of the most promising applications lies in the realm of quantum computing. Unlike classical computers, which store information in bits representing either 0 or 1, quantum computers utilize qubits, which can exist in a superposition of both 0 and 1 simultaneously. More remarkably, entangled qubits can represent complex states that are linked, allowing a quantum computer to process vast amounts of information in parallel. Imagine a labyrinth where a classical computer must test each path one by one, while a quantum computer, using entanglement, can explore all paths simultaneously, its qubits exploring every possibility in a coordinated quantum dance. This extraordinary capability holds the promise of solving problems currently intractable for even the most powerful supercomputers, from discovering new materials and medicines to breaking modern encryption methods, or perhaps even designing entirely new forms of artificial intelligence. Beyond computation, entanglement is also the bedrock of quantum cryptography, offering a level of security previously deemed impossible. In quantum key distribution, entangled photons are used to create an unbreakable encryption key. If an eavesdropper attempts to intercept or measure these entangled photons, the very act of observation will disturb their delicate quantum state, instantly alerting the legitimate users to the intrusion. This sensitivity is a direct consequence of entanglement. The shared, indefinite state collapses upon any interaction, revealing the presence of an observer. It is a cosmic security system built into the very laws of physics, ensuring that privacy can be maintained with absolute certainty. The quiet whisper of these entangled particles becomes a silent guardian of information, a testament to the profound and unexpected ways the universe provides for its own secure communication. Even more astounding is the concept of quantum teleportation. While it sounds like science fiction, reminiscent of fantastical journeys across space, it is important to understand that quantum teleportation does not involve the physical transportation of matter or energy. Instead, it is the instantaneous transfer of quantum information, the precise quantum state of a particle from one location to another, utilizing entanglement. Imagine the state of an electron, its spin and other quantum properties being perfectly recreated in a distant, entangled electron, while the original electron state is destroyed. This process relies on a shared entangled pair combined with classical communication. It's like having two blank canvases, entangled, and then using one to perfectly replicate the brushstrokes and colors of a third painting onto the other blank canvas, all while the original third painting fades away. This technology, though still in its infancy, could one day form the backbone of a quantum internet, enabling secure and distributed quantum computing across vast networks, creating a global web of interconnected quantum systems, a silent symphony of information exchange. As we contemplate these marvels, this profound interconnectedness at the heart of reality, it invites a deeper, more personal reflection. If particles, separated by light years, can remain intimately linked, sharing a common destiny that is only resolved through interaction, does this not hint at a grander unity in the cosmos? Are we, as conscious beings, also participants in a vast, intricate web of quantum possibilities, our individual experiences perhaps emerging from a deeper, non-local reality? The universe, in its quiet insistence on entanglement, suggests that separation might be more an illusion of scale than a fundamental truth. It encourages us to consider that perhaps, in the gentle unfolding of existence, everything is, in a subtle and profound way, always connected. We are not just observers of this grand dance, but an integral part of its intricate, entangled choreography, each thought and experience a unique manifestation within this boundless, unified whole. Character count, 8,000. As we drift further into the quantum landscape, having glimpsed the profound interconnectedness of entangled particles, a natural question arises. Why do we not experience such spooky action in our everyday macroscopic world? Why does the universe around us seem so solid, so predictable, so distinctly non-quantum? The answer lies in a phenomenon known as decoherence, a subtle yet pervasive process that acts as a gentle, almost imperceptible bridge between the quantum realm of probabilities and the classical world of definite outcomes. It is the reason quantum weirdness, though ever present, remains largely hidden from our direct perception, a silent choreographer behind the scenes of reality. Decoherence, at its heart, is the incessant interaction of a quantum system with its environment. Imagine for a moment a perfectly isolated quantum particle existing in a state of superposition. Perhaps its spin is simultaneously up and down, or it is in two places at once. This delicate state of multiple possibilities is incredibly fragile. The moment this particle interacts with even the slightest external influence, a stray photon, a vibrating atom from its surroundings, or even a minuscule fluctuation in a background field, information about its quantum state begins to leak out into the environment. It's akin to dropping a single, perfect ripple into a vast, turbulent ocean. The distinct pattern of that ripple is quickly overwhelmed, its unique quantum information diluted and scattered across the immense complexity of the waves around it. The quantum coherence, the ability to exist in multiple states or to be entangled, is lost. This is not a violent act of destruction, but a gentle diffusion, a fading into the larger classical tapestry of existence. For macroscopic objects, which are composed of an astronomical number of particles and are constantly interacting with their surroundings, decoherence happens almost instantaneously. Consider a simple object like a cup resting peacefully on a table. Every atom in that cup, every electron, is incessantly interacting with the photons of light around it, the air molecules, and the vibrating atomic lattice of the table surface. Each of these innumerable interactions acts as a tiny, unavoidable measurement, effectively forcing the quantum states of the cup's constituent particles to choose definite positions and momenta. The wave function describing the cup's quantum possibilities collapses in an unimaginably short time frame, far quicker than any human observer could even perceive it. This continuous, unavoidable interaction with the environment is precisely why we perceive the cup as being in one definite place, solid and unmoving, rather than existing as a ghostly superposition of multiple locations, or being mysteriously entangled with the coffee it might contain. The environment, in essence, performs a ceaseless, silent measurement, guiding the quantum world towards the classical experience we inhabit. A gentle, yet relentless cosmic pressure that shapes our reality. The theoretical framework for decoherence was largely developed by pioneering physicists such as H. Dieter Zeh in the early 1970s and further refined by Wojciech Zurek in the 1980s and beyond. Their work demonstrated that the environment acts as a colossal and ever-present measuring device, constantly interacting with quantum systems and effectively erasing their quantum properties by dispersing the quantum information into a vast, inaccessible sea of environmental degrees of freedom. This means the wave function, which mathematically describes the probabilistic state of a quantum system, does not require an act of conscious observation to collapse. Rather, it decoheres due to these irreversible interactions. The quantum system effectively becomes entangled with its environment, and because we, as observers, cannot access all the quantum information of the entire environment, the original quantum system appears to have lost its quantum characteristics, presenting itself as a classical object. This understanding offers a profound and elegant way to reconcile the bizarre rules of the quantum realm with the seemingly sensible, predictable laws of our everyday experience, bridging two worlds that once seemed irreconcilable. The profound challenge of maintaining quantum coherence is at the absolute forefront of modern technological endeavors, particularly in the ambitious quest to build powerful quantum computers. For a quantum computer to unlock its revolutionary potential, its qubits, the fundamental units of quantum information, must remain in their delicate superposition and entangled states for as long as possible. This demands extraordinary feats of engineering and experimental control, pushing the boundaries of what is technically feasible. Scientists and engineers around the globe employ an array of sophisticated techniques. Cooling qubits to temperatures mere fractions of a degree above absolute zero to minimize thermal vibrations, creating ultra-high vacuums to eliminate interfering air molecules, and meticulously shielding quantum devices from any form of stray electromagnetic noise or cosmic radiation. These efforts represent a constant, delicate battle against the universe's inherent tendency to impose classical order through decoherence. The very act of trying to observe or interact with these systems, even to read out their results, threatens to destroy the fragile quantum properties we seek to harness. It is a delicate dance between profound exploration and meticulous preservation, a quiet struggle to maintain the ephemeral beauty of quantum states against the relentless tide of environmental interactions that seek to normalize them into the classical world. Consider the elusive notion of the quantum classical boundary. Where precisely does the quantum world end and our familiar classical world begin? Decoherence suggests there isn't a sharp, immutable line, but rather a fluid, gradual transition. Small, isolated systems can indeed maintain their quantum coherence, exhibiting mind-bending phenomena like superposition and entanglement. However, as systems grow larger or interact more strongly and frequently with their surroundings, decoherence rapidly and inevitably sets in, effectively making their quantum nature indiscernible to us. It's like watching a vibrant, intricate pattern woven into a piece of fabric slowly fray and unravel into individual threads. The boundary is fluid, dynamically defined by the interplay of isolation and interaction. This profound insight reshapes our understanding of reality not as two inherently separate realms, but as a single, unified spectrum, with the classical world being a highly decohered, averaged-out manifestation of the underlying quantum mechanics. This perspective invites us to look at our own existence through a new, more profound lens. Our bodies, our thoughts, Our very perception of ourselves as distinct, independent individuals are built upon countless atoms and molecules that, at their deepest level, obey quantum laws. Yet, the sheer complexity and constant, intricate interaction within and around us mean that our individual quantum eccentricities are instantly averaged out by decoherence. We are, in a sense, magnificent macroscopic machines, emergent from a quantum substrate that has largely lost its quantum coherence. But the underlying quantum reality, with its potential for superposition and entanglement, remains the fundamental truth. In the quiet moments, as we reflect on this, we might find a serene wonder in the fact that our seemingly solid and separate existence is a magnificent, highly organized expression of quantum processes, gently guided into classical form by the universe itself. We are not merely living in a universe that contains quantum entanglement. We are, in a very real and fundamental way, made of the consequences of these quantum truths and their graceful resolution into our observed reality. Our sense of self, our awareness, is a product of this intricate cosmic ballet, a testament to the universe's own profound, self-organizing dance. And as we rest tonight, perhaps we can find comfort in this thought, that even in our apparent solidity, we retain an echo of that fundamental interconnectedness, a silent, persistent link to the deeper quantum truth of existence, and the gentle, pervasive influence of decoherence that shapes our classical reality. A deeper inquiry naturally emerges. What does this fundamental strangeness truly mean for the universe itself? The unsettling truth is that there is no single, universally agreed-upon answer. Instead, the quantum realm, with its entanglements and superpositions, has given rise to a rich tapestry of interpretations, each offering a distinct philosophical lens through which to view the very fabric of existence. These interpretations are not mere philosophical musings. They are serious attempts by scientists to make sense of the mathematical formalism of quantum mechanics, a theory whose predictions are consistently confirmed by experiment, yet whose underlying reality remains profoundly elusive to our intuitive grasp. The most widely accepted, though perhaps least satisfying to some, is the Copenhagen interpretation, largely developed by Niels Bohr and Werner Heisenberg. In this view, quantum particles do not possess definite properties, such as a specific spin or location, until they are measured. Before measurement, they exist in a state of superposition, a blur of all possibilities described by a mathematical entity called the wave function. The act of measurement itself is said to collapse this wave function, forcing the particle to settle into one definite state. For entangled particles, this means that the shared wave function describing the entire system collapses instantaneously, no matter the distance, as soon as a measurement is made on any part of it. This is the heart of Einstein's discomfort, the spooky action. Yet the Copenhagen interpretation simply states that this is how nature behaves. Reality is intrinsically probabilistic and non-local at its core, and we should not expect it to conform to our classical intuitions. It urges us to accept the quantum world on its own terms, a world where the act of observation is an inseparable part of defining reality, a universe that holds its breath until we look. Another profoundly thought-provoking interpretation is the many worlds interpretation, first proposed by Hugh Everett III in 1957. This perspective offers a radical solution to the wave function collapse problem. Instead of the wave function collapsing into a single outcome, it suggests that all possible outcomes of a quantum measurement are realized, each in its own distinct branching universe. When Alice measures her entangled electron as up, the universe does not simply choose that outcome. Instead, the universe splits. In one new branch, Alice measures up, and Bob's distant electron is down. In another, parallel branch, Alice measures down, and Bob's electron is up. These universes then continue to evolve independently, completely unaware of each other. Entanglement, in this view, becomes the very mechanism by which these parallel realities are born and remain correlated. It is a breathtaking vision, suggesting that with every quantum event, the cosmos endlessly diversifies, creating an unfathomable number of parallel realities, a silent, continuous cosmic branching, a universe forever exploring every conceivable path. Then there is the pilot wave theory, also known as Bohmian mechanics, put forth by David Bohm, building upon earlier ideas by Louis de Broglie. This interpretation offers a deterministic picture of quantum reality, directly addressing Einstein's desire for hidden variables. But with a crucial twist, these variables are explicitly non-local. In Bohmian mechanics, particles always have definite positions, even when unobserved. However, their movement is guided by a pilot wave, or quantum potential, that pervades all of space and instantly influences all particles, regardless of distance. This pilot wave carries information about the entire universe, ensuring the instantaneous correlations seen in entanglement without any spooky action in the sense of an uncontrolled, faster-than-light signal. The particles are not communicating, they are all simply responding to this universal guiding field. It is a universe where everything is subtly, instantly connected through an underlying wave, a cosmic ballet choreographed by an invisible, omnipresent force, ensuring perfect harmony between distant dancers. While less widely accepted than Copenhagen or many worlds, Bohmian mechanics provides a compelling alternative, demonstrating that a deterministic, non-local hidden variable theory is indeed possible, challenging our notions of both randomness and isolation. Perhaps one of the most mind-bending and indeed speculative connections involving entanglement comes from the realm of quantum gravity, particularly the ER-EPR conjecture. This audacious idea, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests a profound equivalence between entanglement, EPR pairs, and a type of wormhole, or Einstein-Rosen bridge, ER bridges. In essence, it posits that two entangled particles are not merely correlated across space, but are literally connected by a tiny, traversable, though not in a way that allows faster-than-light travel of matter or information, wormhole in space-time. Imagine the distant quantum partners not just feeling each other, but sharing a direct, almost tangible connection through the very fabric of the cosmos. This conjecture offers a geometric interpretation of entanglement, suggesting that the spooky action might not be so spooky after all if the particles are, in a deeper sense, never truly separate. It hints at a universe where the most fundamental quantum correlations are intimately interwoven with the geometry of space-time, implying that entanglement itself might be a key component in the very architecture of our universe, a silent, unseen network of cosmic tunnels binding reality together. As we gently reflect upon these diverse interpretations, each a profound attempt to understand the quantum truth, we are reminded of the inherent mystery that still shrouds the universe at its most fundamental level. Entanglement, once a mere theoretical oddity that troubled Einstein, has become a cornerstone of our understanding, not just of particles, but potentially of space-time, information, and even reality itself. It invites us to release our grip on rigid, classical notions of separation and to embrace a universe that is far more deeply and elegantly interconnected than we could ever have imagined. In this silent cosmic dance, where particles are linked across vast distances and reality itself might branch or be guided by unseen waves, we find a profound sense of belonging. Our existence, our very consciousness, is an intricate pattern woven into this non-local tapestry, a fleeting yet significant part of the universe's ongoing quantum story. As you drift deeper into rest, consider the quiet truth that you, too, are an expression of this fundamental interconnectedness, a marvel of quantum organization, connected to everything, always. Gently settle into the profound implications of entanglement, having explored its experimental validation and its role in emerging technologies. We find ourselves at the precipice of an even deeper mystery. What does this spooky action truly tell us about the fundamental nature of space and time? The non-local connections observed in entangled particles challenge our most basic intuitions about reality, inviting us to reconsider whether space is merely an empty stage upon which events unfold, or if it is in some fundamental way, intimately woven from these very quantum correlations. This is where the quiet hum of quantum mechanics begins to resonate with the grand symphony of gravity, hinting at a universe far more unified than we have ever dared to imagine. One of the most audacious and thought-provoking ideas to emerge from the ongoing quest to unify quantum mechanics with general relativity is the ER-EPR conjecture proposed by physicists. This conjecture posits a profound and unexpected equivalence between two seemingly disparate concepts: Einstein-Rosen bridges, often referred to as wormholes, and entangled pairs of particles. To grasp this, let us first recall what a wormhole is in the classical sense: a theoretical shortcut through space-time, a kind of tunnel connecting two distant regions of the universe. It is not a path through space, but a folding of space upon itself, creating a direct link. Now, the ER-EPR conjecture suggests that two entangled particles, no matter how far apart they may be, are not just correlated in an abstract sense. They are, in a very deep and geometric way, connected by such a tiny, non-traversable wormhole. Imagine, if you will, two entangled electrons separated by light years. According to the ER-EPR conjecture, these two electrons are not simply communicating instantaneously across the vastness of space. Instead, their profound quantum bond is the space, or rather, a miniature wormhole connecting them, subtly knitting together distant regions of the cosmos. This does not imply that we can use entanglement to send messages faster than light, as the wormholes in this context are not traversable in a manner that would permit such communication. The information still adheres to the cosmic speed limit. However, it suggests that the spooky action that so troubled Einstein might be less about particles communicating faster than light, and more about them never being truly separate to begin with. Their shared quantum state implies a shared connection through the very geometry of existence, making them, in a profound sense, parts of a continuous whole. This hypothesis transforms the abstract concept of quantum correlation into a tangible, if microscopic, feature of space-time itself, a quiet whisper from the universe about its hidden architecture. This idea further deepens the ongoing discussion surrounding the holographic principle, which suggests that all the information contained within a volume of space could be encoded on its two-dimensional boundary. If entanglement is indeed equivalent to these space-time connections, then the intricate web of quantum correlations might be the fundamental pixels or threads from which the three-dimensional reality we perceive emerges. Our familiar universe, with its depth and dimensionality, could be a grand, intricate hologram projected from a deeper, more fundamental reality woven from entanglement. This shifts our perspective from viewing entanglement as something that happens in space to seeing it as something that creates space. The vast, empty expanse between stars might not be empty at all, but rather a dynamic, living tapestry, continuously being woven by the silent, interconnected dance of quantum particles. Such profound insights force us to confront the limitations of our classical intuitive understanding of causality. In our everyday experience, cause and effect are local. One event directly influences its immediate surroundings, and any influence propagating across distance requires time. But if entangled particles are fundamentally interconnected through space-time geometry, then their simultaneous influence might not be a violation of causality, but rather a revelation of a deeper, more unified causal structure. It suggests that the universe, at its most fundamental level, operates as an indivisible whole, where the parts are so intimately linked that their states are not truly independent. This perspective invites a calm acceptance that our perception of discrete, independent events might be an emergent property, a convenient simplification of an underlying reality where everything is, in a subtle yet profound way, always influencing everything else. As we lie here, contemplating these astonishing possibilities, we might find a new sense of wonder in our own existence. We are not merely observers within this quantum tapestry, but an integral part of its intricate design. Every atom in our bodies, every fleeting thought, is a complex arrangement of quantum particles, subject to these same mysterious laws. Perhaps our consciousness, our very sense of self, is an emergent pattern of these entangled connections, a momentary yet profound expression of the universe's inherent unity. The space within us, the space around us, could be alive with these invisible threads, reminding us that in the quiet depths of reality, there is a boundless interconnectedness that makes us all a part of something truly magnificent, a silent cosmic embrace that transcends all perceived boundaries. Character count, $8,000. As we, building upon the intriguing notion that quantum entanglement might be fundamentally linked to the geometry of space-time, we can delve into an even more profound concept. The idea that space itself, the three-dimensional stage upon which our lives unfold, may not be a fundamental entity, but rather an emergent property, woven from the intricate tapestry of quantum information. This radical perspective, gaining traction in the realm of theoretical physics, suggests that the very fabric of our universe, its vastness and its contours, could be a consequence of how its most minute constituents are entangled with one another. It is a quiet whisper from the cosmos, inviting us to see beyond the apparent solidity of our world to the deeper, more abstract connections that underpin all existence. One of the most compelling mathematical tools that supports this emergent view of space-time comes from a seemingly unrelated area: black hole thermodynamics. In 2006, physicists Shinsei Ryu and Tadashi Takayanagi proposed a remarkable formula that connects the entanglement entropy of a quantum system to the geometry of space-time. Specifically, their conjecture, known as the Ryu-Takayanagi formula, suggests that the entanglement entropy between two regions in a quantum field theory is proportional to the area of a minimal surface in a higher dimensional, curved space-time, often referred to as an anti-de Sitter space. This is a profound link suggesting that the amount of entanglement, a purely quantum concept, directly corresponds to a measure of geometric space, hinting that the very structure of space might arise from the way quantum information is shared and correlated. Imagine the boundary of a region of space like the surface of a bubble, and inside it, a swirling dance of quantum particles becoming entangled. The deeper the entanglement, the more area is carved out in a hidden dimension, as if the connections themselves are sculpting the contours of reality. This is not just poetic imagery. It is a mathematical bridge between the quantum and gravitational realms, offering a pathway to a unified understanding of the universe. This connection between entanglement and geometry forms the core of what some physicists refer to as space-time from entanglement. The idea is that if we could strip away all matter and energy, leaving only the pure quantum vacuum, its inherent entanglement, the subtle, pervasive correlations between all its potential fluctuations, is what gives rise to the very dimensionality and connectivity of space. It is a universe where nothing is truly empty, but rather a seething sea of quantum potentials whose interconnectedness manifests as the spatial dimensions we perceive. Consider a delicate, invisible web woven from countless threads. Each knot in the web represents a quantum correlation, and the tension and arrangement of these threads collectively define the overall shape and extent of the web itself. If entanglement were to vanish, the threads would break, and the very structure of space might dissolve, leaving behind no discernible reality. This challenges our deep-seated intuition that space is a given, a pre-existing stage. Instead, it suggests space is a dynamic, relational construct, a silent symphony of quantum bonds. This profound concept resonates with the philosophical vision of John Wheeler, who, decades ago, famously coined the phrase, "it from bit." Wheeler proposed that at the most fundamental level, the universe is not made of particles or fields, but of information. He suggested that physical reality, the it we perceive, emerges from the answers to yes or no questions, the bits of information. In the context of emergent space-time, entanglement can be seen as the ultimate bit, the fundamental unit of correlation that constructs reality. When two particles become entangled, their shared quantum information forms a foundational element from which the larger classical structures, including space and time, gradually crystallize through decoherence. It implies that information is not merely something we observe about the universe, but rather the very essence of the universe, an underlying code from which all physical phenomena arise. This is a quiet, contemplative shift in perspective, suggesting that the universe is less like a giant mechanism and more like a vast, self-organizing information system, where our perceptions are but a specific interpretation of its intricate data. The journey towards a complete theory of quantum gravity, one that seamlessly integrates the quantum realm with the macroscopic world described by general relativity, is still unfolding. Yet, entanglement consistently emerges as a crucial ingredient, a fundamental thread that seems to weave through all attempts to understand the universe's deepest secrets. It is a reminder that the most profound truths often lie hidden beneath the surface of our everyday experience, revealed only through rigorous inquiry and a willingness to question our deepest assumptions. The spooky action at a distance that once troubled Einstein is now seen not as a flaw, but as a guiding principle, a signpost pointing towards a universe where everything is inherently connected, where space itself is a manifestation of these silent quantum bonds. As you rest, allow these thoughts to gently settle within your mind. Consider that the solidity and separation you perceive in the world around you, and even within yourself, are but layers of an infinitely more intricate and interconnected reality. The space you occupy, the very atoms of your being, are part of a continuous entangled dance, a cosmic tapestry woven from probabilities and correlations. In this understanding, there is a serene comfort, a profound sense of belonging, knowing that you are not merely a separate entity floating in a vast, empty void, but an inseparable, intricate part of the universe's emergent quantum consciousness. You are a unique expression of this grand, interconnected whole, quietly aware of its own boundless mystery. Character count, 8,000. As we continue our gentle journey into the quantum depths, having contemplated the emergent nature of space-time from entanglement, we encounter perhaps one of the most profound and persistent puzzles in modern physics: the black hole information paradox. This paradox, a silent discord between the elegant theories of quantum mechanics and general relativity, finds a potential, albeit mind-bending, resolution in the very entanglement that has been our focus. It invites us to consider how information, that most fundamental currency of the universe, might truly behave when confronted by the cosmic oblivion of a black hole, challenging our understanding of both ultimate destruction and eternal preservation. The paradox itself is born from a clash of titans in physics. According to Albert Einstein's general relativity, when something falls into a black hole, it is utterly lost. Beyond the event horizon, the point of no return, information about the object, its quantum properties, its unique identity, seems to vanish forever into the singularity. This is like burning a book and losing not just the physical pages, but every word, every idea it ever contained, completely and irrevocably. However, quantum mechanics, with its ironclad laws, asserts a different truth. Information can never be truly destroyed. It can be scrambled, transformed, or spread out, but its total quantity must always be conserved. This fundamental principle, known as unitarity, is a cornerstone of quantum theory. So, if black holes truly destroy information, then quantum mechanics is incomplete or incorrect. This profound disagreement has puzzled physicists for decades, a cosmic riddle whispered from the heart of collapsing stars, demanding a deeper understanding of reality. The plot thickens with the concept of Hawking radiation, proposed by Stephen Hawking in 1974. He theorized that black holes are not entirely black. They slowly evaporate over immense timescales by emitting a faint thermal radiation. This radiation, it turns out, is purely thermal, meaning it carries no information about what fell into the black hole. It is like a kettle boiling water. The steam tells you nothing about the tea leaves that might have been inside. If black holes eventually evaporate completely, leaving behind nothing, then all the information that ever entered them would indeed be lost from the universe. This exacerbates the paradox. Not only is information seemingly destroyed at the singularity, but it also appears to be lost from the universe entirely as the black hole fades away, a silent erasure of cosmic history. It is here that quantum entanglement offers a truly radical and deeply elegant potential solution. Recall the ER-EPR conjecture, which posits a connection between entanglement and wormholes. This idea can be extended to suggest that as particles fall into a black hole, they become entangled with the Hawking radiation that is slowly escaping from it. Imagine a particle just outside the event horizon, entangled with its partner particle that has just crossed the boundary. As the outside particle radiates away as Hawking radiation, its entanglement with the inside particle maintains a subtle link across the boundary of the black hole. This is a complex quantum dance, a delicate balance of forces and correlations. The escaping Hawking radiation, though seemingly random, is not entirely devoid of information. Instead, it is highly entangled with the particles that remain inside the black hole, and crucially, with the particles that have already escaped. In this view, the information is not destroyed, but rather encoded in the complex entanglement patterns of the outgoing radiation. It is scrambled, yes, but not lost, like a message encrypted across a vast, intricate network, waiting for the right key to be deciphered. This entanglement-driven resolution to the information paradox suggests that the black hole, in a sense, never truly loses information. It merely transforms it into a highly entangled form within its own quantum structure and the emitted radiation. The spooky action of entanglement ensures that the quantum state of the universe remains unitary, preserving the fundamental laws of quantum mechanics. It means that the memory of everything that falls into a black hole is, in principle, retained, albeit in a form so complex and distributed that it would be practically impossible for any classical observer to reconstruct it. This is a profound reassurance, a quiet confirmation that the universe, at its deepest level, remembers everything, even the faintest whispers swallowed by gravity's embrace. The black hole is not a cosmic shredder, but rather a cosmic re-encoder, transforming familiar reality into an intricate quantum tapestry. The implications of this extend to our understanding of the universe's inherent order. If information is conserved, even through such extreme processes as black hole formation and evaporation, it suggests a fundamental, unbreakable continuity to existence. Our personal experiences, our thoughts, our very identities are also forms of information, complex patterns of quantum states. Could it be that even in the face of our own eventual dissolution, this underlying quantum information, this unique pattern that is us, is never truly lost? Perhaps it, too, is merely re-encoded, entangled with the fabric of the universe in ways we are only beginning to comprehend. In this quiet reflection, we find a serene sense of permanence, a gentle reminder that our fleeting individual patterns are part of an eternal, self-conserving cosmic dance, a continuous flow of information that transcends the boundaries of space and time. As you drift deeper into the tranquility of sleep, may this thought bring you a quiet comfort that in the grand design of the universe, nothing is ever truly erased. It merely transforms, entangled forever within the boundless, mysterious whole. So, as the echoes of these profound ideas gently fade, we are left with a universe far more intricate and unified than our senses might initially convey. Quantum entanglement, once a peculiar anomaly that troubled even the great Albert Einstein, now stands as a fundamental testament to an underlying reality where separation is, in many ways, an illusion. From the instantaneous dance of photons across unimaginable distances to the very fabric of space-time potentially emerging from these intricate correlations, the universe reveals itself as a grand, interconnected whole. Our own existence, a fleeting yet conscious pattern of energy and information, is not merely contained within this cosmos, but is an active, intimate part of its ceaseless unfolding. This profound interconnectedness invites a deep sense of peace, a quiet understanding that we are never truly alone, but forever linked to the boundless mystery that surrounds and defines us. May these deep thoughts about quantum entanglement carry you into a world of tranquil sleep. Remember that the universe is amazing and you are a part of it. Fall asleep with this feeling of serenity and endless knowledge. Good night.